In this section, I'm going to be reviewing buffers, so how to determine the pH of a buffer solution given concentrations of acid and its conjugate base or base and its conjugate acid. And we'll also look a little bit into what happens when we add a strong acid or a strong base to a buffer and how that changes the pH. So a buffer is a mixture of a weak acid and its conjugate base that resist pH changes when small amounts of acid or base are added to the solution or when the buffer is diluted. So neither of those two conditions should change the pH very much at all. So the whole point of a buffer is to have a system or have a solution that does not change pH very much. So buffers are important in several different instances. If you want to talk about living organisms, enzymes within our bodies have to operate at specific pH values in order for them to actually do what they're supposed to do. If the pH of our blood, for example, falls outside of those optimum pH conditions, the enzymes won't do what they're supposed to do. They won't work properly. Another buffer system that you will find would be something in a lake or a river, so an environmental buffer. If the lake or river bed is composed of limestone, then there's going to be some carbonate in that river or lake, and that is going to help buffer or reduce pH changes if that lake or river, for example, is in an area where acid rain is a thing. So we're going to go back to general chemistry 2 for a second and talk about Le Chatelier's principle and relate that to buffers. So remember, Le Chatelier's principle states that when you stress a reaction at equilibrium, that equilibrium is going to shift in a direction to try and reduce that stress. So for example, if you have a reaction at equilibrium, you add some reactants to that equilibrium, the reaction wants to try and remove that stress, so remove some of those reactants that you've added to it, and in order to do that, it will shift to make more products because that's how it's going to get rid of those excess reactants. So in terms of a buffer, we know that it is composed of both a weak acid and a weak base, and they have to be at reasonably high concentrations, maybe 10 to the minus 3 molar and higher, something like that. And they have to be at relatively equal concentrations, usually plus or minus a factor of 10 from each other in order for that system to actually work as a buffer. So we also know that these reactions are equilibrium reactions because they have the equilibrium arrows, and weak acid, weak base reactions are very reactant favored, which means they don't dissociate, they don't ionize very much. So what if we have the first reaction, HA in equilibrium with H plus and A minus? We know that doesn't ionize very much, but then what if we add the weak acid A minus to that particular reaction? It already doesn't ionize very much, but what we're essentially doing is adding a product to that reaction. So if we're adding A minus to that first reaction, what's that going to shift the reaction towards? It's going to shift it towards the reactants. So it's going to make more HA. Now we know A minus doesn't react much with water either. So if we had that second reaction and we added HA to that, we're doing the same thing. We're adding a product which is going to shift the reaction towards A minus. Now in a buffer, we have both of these reactions happening at the same time because we have a bunch of HA, we have a bunch of A minus in solution at the same time. They're both in equilibrium with each other through both of these reactions, and because they don't ionize much, and because we've added products to both of those reactions in terms of the HA or the A minus, then these weak acids and bases aren't ionizing very much at all. They're ionizing even less than they would if they were just there on their own. So when we have a buffer solution, we essentially end up with the same concentrations of weak acid and weak base as we put into that particular reaction. So if we put in 0.1 moles of HA, 0.1 moles of A minus, we end up with approximately 0.1 moles of HA and A minus in solution because neither of them is ionizing very much to produce their respective products. So to figure out the pH of a buffer, we use what's called the Henderson-Hasselbalch equation. Again, you've seen this before in general chemistry too. So the form of it that you usually see is this one here, although the one below it is pretty much the same, just using slightly different notation. So the two pieces of information we need for the Henderson-Hasselbalch equation are the pKa, so that's the pKa of the acid, right? We have a Ka, which means we're talking about the acid. And we need the concentrations of the weak base and the weak acid. And remember, the pKa refers to the acid in that particular equation. So let's look at the Henderson-Hasselbalch equation and assume that we have equal concentrations of both the weak acid and the weak base in this buffer. So here's our Henderson-Hasselbalch equation. If we have equal concentrations of A- and HA, that fraction is going to equal 1. And what's the log of 1? The log of 1 is 0. So if we have pH equals pKa plus the log of 1, we end up with pH of that solution is going to be equal to the pKa of the acid if we have equal concentrations of the acid and the base. So this ratio of A- over HA is going to determine what the pH of a buffer solution is, or how it changes based on both of those concentrations with respect to the pKa. So the pKa of an acid is kind of the starting point of where that pH should be. So you assume we have equal concentrations of acid and base. pH of the solution is going to equal pKa. But now what if we have a higher concentration of base? So a higher concentration of A-. So we start off here a 1-to-1 where pH equals pKa. And if we have 10 times more base than acid, we're going to have a 10 on the top of the fraction and say a 1 at the bottom there because we have 10 times more base. Now we have a log of 10, and the log of 10 is now 1, so the pH of this solution is going to be the pKa plus 1. It makes sense because we have more base. The pH of the solution should be more basic than what it would be if we had equal concentrations of acid and base in the solution. And since pH is a log scale, every time the ratio changes by a factor of 10, the pH is going to change by 1 unit. So we're going to increase again the concentration of base by another factor of 10, so now it's 100 times more base than acid. So we'd have 100 as A-, 1 as HA. Now we have log of 100, which is 2, so we have pH equals pKa plus 2. And if we go in the opposite direction, we have more acid than base, then we're just going to have the opposite trend because we're going to have the log of 0.1 in the case of this here. The log of 0.1 is -1, and the log of 0.01 is -2. So that ratio is going to determine how the pH changes. So the ratio of A- over HA is going to determine how far away the pH of the solution is compared to the pKa of the acid. The more base there is, the more basic the solution will be. The more acid there is, the more acidic the solution will be. So let's just go through a quick practice. So what is the pH of a buffer prepared by dissolving 0.1 moles of weak acid plus 0.05 moles of its conjugate base in 1 liter? So we're given a Ka, 2.3 times 10 to the minus 5, and we're also given the moles of both the acid and its conjugate base. And we can figure out concentration pretty easily because the solution is in 1 liter, so the moles is just going to be the concentration really, right? 0.1 moles in 1 liter is 0.1 molar. So in order to figure out the pH, we first have to figure out what the pKa is. So pKa equals negative log of Ka equals negative log 2.3 times 10 to the minus 5, and that equals 4.64. Now to figure out the pH, we simply use the Henderson-Hasselbalch equation. pH equals pKa plus log A- over HA, and that's going to equal 4.64 plus log, and our concentration of A- is 0.050 molar divided by 0.100 molar, and then that gives us a pH equal to 4.33. Okay, it makes sense. We have more acid than we do base, so the pH should be less than 4.64 because that's our starting point, right? This ratio over here is just modifying this number here. We're just telling us, is our solution going to be more or less acidic than that particular number there? So we have more acid, we have to be on the acidic side of the pKa. If we had more base, we'd have to be on the basic side of the pKa. So let's try another example. Find the pH of a solution prepared by dissolving 1.23 grams of tris plus 2.86 grams of tris hydrochloride in 1 liter of water, and we're given the pKa. So we're looking at this particular reaction here in the bottom. We're given the acid as the tris HCl and the base as the tris. So the first thing we have to do is to find the concentrations of each of the tris and the tris HCl. So to do this, we're given the mass of the tris, we're given the molar mass, so that's going to give us how many moles per liter. So for tris, when we do this calculation, we end up with 0.0105 molar, and for tris HCl, we get 0.01815 molar. Okay, so now we just plug in the numbers into the Henderson-Hasselbalch equation to determine the pH. In the previous slide, we're given the pKa as 8.07. We just solved for B, which is the tris, BH plus, which is the tris HCl, and if we solve that equation, we end up getting a pH of 7.81. Now, if we look at the pKa being 8.07, in this particular question, we have more acid than we do base, so our pH should be on the acidic side of the pKa, right? It's less than the pKa, and that's what it is. Now, we didn't really have to worry about finding concentrations. We can also use just moles in the Henderson-Hasselbalch equation right here. Now, why can we just use moles? Well, it doesn't really matter if we put a volume in there, if it's moles per liter or moles per 4.687 milliliters, whatever number you choose there. Both the concentration of the acid and the base are going to have that same number as the volume, so they just end up canceling each other out. They're not going to affect the ratio of base over acid. So whether you use concentration or moles, it's not going to make any difference at all. So the volume of the solution is irrelevant to finding the pH. It doesn't matter what the volume is. As long as you know how many moles of acid and base are in there, then your pH calculation will be the same using the Henderson-Hasselbalch equation. Now, what if we have that buffer that was prepared in the previous slide with a pH of 7.81, and we added some HCl to it? How is that going to change the pH? So I've set up a table just to show how this would work. And the thing to realize when adding a strong acid or a strong base to a buffer is that the strong acid or the strong base, they both react completely in the reaction with the acid or the base, right? The strong acid is going to react with the weak base. If you were added a strong base, that would react with the weak acid. So in this case, we're adding a strong acid, so it's going to react with the weak base, which is the tris. So we got to figure out how many moles of acid we've added, and we've added 3 milliliters of 1 molar hydrochloric acid, and if we figure out how many moles it is, it ends up being 0.003 moles. And if that reacts completely with the weak base, that's shown on the second line of this table. We have the tris that we started off with, and it's reacting with the HCl, and it's reacting completely, so there's going to be no HCl remaining. So all the HCl is going to go away. It's going to react with the tris, and what's going to happen to that tris? What is that doing? The HCl is adding an H plus to the tris, and it's converting it into tris HCl. It's converting it into the conjugate acid. So we take the amount of conjugate acid, and we add the amount of acid that was added to that reaction. So the H plus is subtracted from the base, but it's added to the acid, the weak acid. So what we end up with is a different number of moles of the tris and the tris HCl. So to figure out the pH of this new solution, we do the Henderson-Hasselbalch equation again, using the same pKa as we had before of 8.07. And this time we have a different ratio of base over acid, and we get a new pH of 7.59. So the previous pH we calculated, the buffer itself was 7.81. We added some acid, the pH goes down to 7.59. That makes sense, it's more acidic. But the other thing to remember is that the pH didn't go down all that much, and that's exactly what a buffer is supposed to do. We added a little bit of strong acid, the pH changes, but it doesn't change by a very large amount. If you were to add the same amount of HCl to just water, water would have a pH of 7 initially. If you added this amount of acid to that, the pH would drop significantly, and it would be approximately 1 or 2. We could calculate what it would be, but the pH would be really low. It would drop by several pH units. Whereas this one, we only dropped by about 0.2 units, 0.3 units. So why does a buffer resist changes in pH? Well, it's because the strong acid that we're adding is being consumed by the weak base, or if we add weak base, it would be consumed by the weak acid. So as long as we don't use up the weak acid or the weak base in the buffer, by adding too much of the strong acid or base, the ratio of the weak base over the weak acid isn't going to change all that much. So that means the pH itself isn't going to change either. As soon as we start adding too much acid or base, too much strong acid or base, then that's when the pH will start to increase rapidly, because we're starting to use up all of the weak acid or the weak base. So the problem with using the Henderson-Hasselbalch equation to calculate the pH of a buffer is it's not quite perfect, because we simplify things when we do these calculations, and we don't consider what is called the activities of the weak acid and the weak base. Now, we're not going to go over this in class, and you probably won't run into this very much in upper level classes. If you do, it'll probably be in physical chemistry. But the activity and concentration are related by ionic strength. So the stronger this buffer is, the more concentrated it is, the more the activity of each of the components is going to matter rather than the concentrations. So we're not going to discuss them, so we can cross out this part here in the slide. So if calculating how to make a buffer is not going to be useful, right? We could calculate how much acid and how much base we need in order to make the buffer, but if that's not going to give us the pH we want, how would we actually do it? Well, I'll tell you also that I don't think anybody really uses the Henderson-Hasselbalch equation in a lab to prepare a buffer. The way we would do it in the lab would be more like this. So if we need a pH 7.6 tris buffer at 0.1 molar concentration and we need a 1 liter solution, the first thing we would do is we would weigh out 0.1 moles of tris HCl and dissolve that in a beaker of approximately 800 milliliters of water. Okay, so our moles of tris HCl is going to equal the moles of buffer that we need, or the concentration of the buffer that we need. And then we're simply going to use a pH electrode to monitor the pH as we add sodium hydroxide to this particular solution. So adding the sodium hydroxide is going to convert some of the tris HCl into the tris, into the base, and that's going to affect the ratio of the acid and the base. So we keep adding sodium hydroxide until the pH reaches 7.6, and then we transfer this to a 1 liter volumetric flask and dilute it to volume. Now remember, diluting a buffer is something that's not going to change the pH very much, because adding water is not going to add very much H+, right? If you remember from general chemistry, the amount of H+ in liquid water is only 1 times 10 to the minus 7 molar. So diluting the buffer isn't going to add enough excess H+ to change the pH of that buffer. So now the buffer capacity is how well a buffer solution resists the changes in pH when acid or base is added. So if you can think of this as the concentration of the buffer. So if buffer has a high concentration, say 0.1 molar versus 0.01 molar. If it's 0.1 molar, there is going to be more weak acid and more weak base available to react with any strong acid or base that is added to that particular solution. If we have a lower concentration, there's less weak acid and less weak base to react with any added strong acid or base. So that's the last point on this slide, the buffer capacity affected by the concentration of the buffer. But buffer capacity is also affected by the pH of the buffer. The buffer capacity will be at its highest when the pH of the solution is the same as the pKa of the buffer, because you can add either strong acid or strong base to the buffer, and the buffer has an equal opportunity to consume that strong base or strong acid. When you choose a buffer that is useful for your situation, you should choose a buffer that has a pKa closest to the pH that you want to prepare. And a useful range of a buffer is usually the pKa plus or minus 1 pH unit. So remember, 1 pH unit represents a factor of 10 in the concentration difference between the acid and the base in that buffer system. So I just want to quickly show you how pH of a buffer changes upon addition of an acid or a base. So if we start on this graph at a pH of 5, so there's the initial pH of 5. Now, what happens to the pH if we add acid? So we know the pH is going to decrease as we add more and more acid, and the change in pH is going to be in this direction. So it's going to be a negative direction in the change of the pH. Now, the spot on this graph where pH equals pKa minus 1 is right around there, and this is pH equals pKa plus 1, right around there. So the useful buffering range is between those two lines. So you can see that in that range, the pH is not changing all that much. So we have a change of that much, approximately, say, 0.05 pH units as we go from the pH of 5 to a pH of 4. Now, if we did the same thing by increasing the pH, we would go from pH 5 to pH 6, and the change is again about the same. Okay, we have approximately a 0.05 difference in the pH from the initial pH of 5 to a pH of 6. Now, once we get outside this range, notice how the pH really starts to change. So from this point here, right on the very edge of the useful buffer range, to the next point. So that represents another increment of H plus added, another 0.01 moles, for example. If each of these dots represents the addition of 0.1 moles of acid, notice that change is about equal to all the previous changes put together. By adding one extra drop or one extra bit of acid, we've decreased the pH by quite a bit. And if we go to the next addition, we've decreased the pH even more. So pH is decreasing even more quickly after that useful pH range. So as we get further and further outside the useful pH range of the buffer, the pH changes much more drastically as we add the same amount of strong acid or strong base. So that's all I have for this section. If you need to brush up a little bit on your buffers, then I suggest you look back at your General Chemistry 2 notes, because you should have gone over buffers quite extensively in that class. But as usual, if you have any questions, feel free to ask.